So you are able to see the screen, right? Okay, so the screen is visible, right? Okay. So anyway, so last class, we have started our last topic, that is this plastic analysis of structures. Okay. So as already we told you, this plastic analysis is very important, especially for steel structures. The reason being, there's a huge ductility. Okay. So this entire ductile thing is there. Then apart from that, say, so compared to your yield strength, you have this ultimate load also is there, which is extremely high, basically. So the steel has, a huge reserve strength, say. So why don't we use this in our design to make our structures more economical? So that is what we discussed in our last class. Okay. And finally, we said that of course, the steel has the plastic thing, and then strain hardening. So many things will be there. So everything is called as plastic itself. Okay. And then what we said was in our conventional analysis, whatever you have studied in your structure analysis or mechanics of materials, so it is based on elastic only. Okay, so there you don't even go into the plastic region. So in steel, say, so you may be more conservatism or something. It will happen in elastic analysis itself. And then when you try to do a real beam, so when the load reaches sigma y, so you can see only the top and bottom only will reach yielding. So you have a lot of structure which is still in elastic range, which we have not utilized basically, okay, in our the classical elastic analysis. So that's why it's a plastic analysis we said, and here we are going to discuss how the structural analysis only. So when it goes beyond the elastic region, so this is what our criterion, and then sigma should be greater than sigma y, how the structure is going to behave. Okay, and then finally we are going to find out something like the load causing complete collapse, say, and then with the we will apply a safety factors of safety and other things. We will work it out. Okay, and the most important thing is this is applicable only for ductile structures. If ductility is not there, this plastic analysis cannot be applicable, and of course more economical things itself. So this is what we said in our last class. And exactly, if you see, if you model the entire stress strain curve of steel, say, so you also will have strain hardening also. It is not only just the plastic thing, but you will have strain hardening. Some more, the reserve strength will come from the strain hardening also. But in our analysis, say, so because this non-linearity and other things are there, so what we do is, we do a simple analysis. We ignore the strain hardening. So our stress strain curve is approximated as simple, a bilinear curve itself, which we call as elastoplastic, the constitutive relation itself. So these how in reality how the failure takes place. And this is what we said about plastic analysis and design. We will make use of the reserve strength and other things. We're trying to do itself. And finally, in the plastic analysis, what we are going to do is essentially moment redistribution only. Okay, so that's what we are going to do here itself. And the most important assumption is one thing is that once any part of a structure, say if it has been stressed to the yield point, okay, so this will not take any additional stresses. Okay, so the additional stresses will be transferred to other parts of a structure or other parts of the cross section, say, which is still in the elastic range itself. So this is the most important assumption. And another assumption is strain hardening we ignore. So simply our stress strain curve is in a simple bilinear curve itself. So these are our assumptions. Okay, and so due to these assumptions, say, so we will go only up to this range only. The strain hardening and other things we ignore. And once it has reached this state, say, we say that plastic hinge has formed and the structure is going to collapse. Okay. And then we have also defined the plastic moment as, so which can produce full plasticities in entire cross section. And of course, it creates a plastic hinge itself. And then the shape factor, which all of you, have studied previously itself, where we said, the shape factor is, this MP by ME, the ratio of plastic to elastic, which we call as a shape factor. Okay. So this is what we said in our last class. And then this also I showed you how to compute elastic moment, how to compute plastic moment over a cross section. We have already discussed when we discussed the beam design and other things also. And finally, these are some of the shape factors, which all of you know, and it is given in the steel tables also. Okay. So plastic analysis essentially hinge formation, the collapse, how the structure is going to collapse. So this you have to see, like how many plastic hinges are required, and estimation of elastic plastic moments, shape factor, load factor, and then collapse load. So this is a broad procedure. So this I showed you in the last class. If you take a simply supported beams, which is a determinate, statically, determinate thing itself. So we all know that, once one hinge say, okay, the where the and this is our bending moment diagram say, okay. So the maximum bending moment is at the just beneath the load itself. So at this point, as the load increases, say, so m, it crosses your yield movement, then the plastification happens, and finally when it reaches MP, say, automatically it tries to collapse itself. And in exactly in a real situation, say, you will see the plastic hinge, it spreads into the neighboring regions, and other things also will happen. Okay. And this is the length of the plastic hinge or something, L by 3 or whatever, you would have studied, in the beam design itself. But in our plastic analysis, what we try to do is we ignore all this length of the plastic hinge and other things also. We say that, as the load increases and, it approaches MP, say, so automatically hinge forms, and then, it breaks into like a rigid kind of, two rigid link kind of a mechanism. Okay. And this is, just the ultimate load for a simply supported beam itself. So this is what we said. So finally, the how the beam is going to find is a rigid link mechanism, which we are going to use itself. And we have also said that, this plastic hinge is only a physical approximation, okay. But in reality, of course, it's a close approximation. We already said in the last class itself. And then we also ignore all these, the length of the plastic hinge, this portion, say, we ignore all these things. Simply, the plastic hinge means it occurs only at a point. So to simplify our analysis, okay. So this we said in our last class. So this is how your beam is going to fail, like a rigid link mechanism. But in reality, if you see, they have shown you the figures also, the beam will not going to behave like this. Okay, in reality, so you will see this type of a hinge mechanisms, which I showed you, in the starting slides. Okay. So this image, so this is how in reality it will be. It will not be like rigid link, breaking it into two pieces or whatever. And you can see plasticity has spread into, a neighboring region also. But in our analysis, we ignore all these things. We model this as a simple point, and it is going to break into like, a rigid link phenomenon. Okay. So these are our assumptions. And then we started discussing indeterminate structure also. So this is a propped cantilever. Okay, the statical indeterminacy is one. Okay, so this is a structure. And then by examining here itself, say, already the bending one diagrams, for this propped cantilever, you would have drawn in, your CA mechanics of materials or structure analysis course itself. So we already know from your elastic analysis, bending moment at A is 3 PL, bending moment at C, that is below the load, say, it is 5 PL by 32. So now with the span is 1, and if you take a 7.5 and 9, say, which comes from the experiments, they would have tested a beam and they would have given these numbers itself. And if we calculate, say, the bending moment at A, bending moment at C, so this is the original diagram for a load of 32 kilonewtons, and this is the deflection basically. Okay. Now for this load, of course, both MA and MCC, they are less than MY. Okay, because MY is 7.5. So everything is perfectly fine. So still everything in the whole beam is in the elastic range itself. Now, as when you increase the load to 40 kilonewtons, say, suddenly what happens is at MA reaches 7.5, that is a yield moment, and plastification starts here. But at our C, say, still it is still in the elastic range itself. Okay, and then if you keep increasing the load to 48 kilonewtons, say, then now the bending moment at this place becomes 9, which is exactly the plastic moment capacity. So that means the whole section has been plastified and a hinge has formed in this region itself. So the first hinge has formed here. Now, although the plastic hinge has formed here, say, the beam is not going to fail because because of redundancies. Now this beam, this cantilever, this fixed support becomes a simply supported. Still, the beam can take some more extra load, although this hinge is formed here because of your indeterminacy. Okay. So now what happens is now the next step of analysis, say, now this is something like, so this hinge, it cannot take more load. That is what our assumption is. Once a section has a plastified, say, since we are ignoring strain hardening and all other things, it cannot take any more extra load at all. Okay, so this becomes like a simple supported beam, here itself. So now when you keep on increasing the load, say, so the extra load that is from 48 to 54 kilonewtons, that will not be taken care by A at all because already it has been plastified. So this whole thing has to be taken care by the remaining portion of the beam, which is the remaining portion of the beam itself. So this extra 6 kilonewtons is here. So now to find out bending moments here, we model this as a simply supported beam. So now after 48 kilonewtons, say, okay, so your propped cantilever has become a simple supported beam. So now for the simple supported beam, PL by 4. So the same expression we use here. And then, now once this MC, so this entire thing will be carried by this MC, that is a moment at C. So now this becomes 9, the kilonewton. And for this, the hinge also gets formed in this portion itself. So now we are having a simply supported beam. And if you have a hinge at the bottom, say, now it cannot take any more load, and at for 54 kilonewtons, say, so your prompt cantilever, collapses itself. So now your deflection, if you try to compute, so the 43.75 comes from the prompt cantilever. Now the extra deflection, say, which is coming from here, so this comes from a simply supported beam. That is, the expression is also, WL cube by, that 48 EI you have to use. So this additional deflection will be this limit, and you can also find out rotation at A because it is a simply supported beam. Say, so you can find out the rotation at A also as some 37.5 some milli, the radians. So this is how the beam collapses. The step by step if you try to do it. So exactly what we have done is, so now at the collapse point, say at P is equal to 54 kilonewtons. If you draw the bending moment diagram, so the bending moment at A also is 9 because it also has plastified, and bending moment at C, this is also is 9 only. So both the things are same, So MA is same as MC, which is 9 kilonewton, because at both the stages, the plastic hinges formed basically. So now this analysis, what we have done is up to 48 kilonewtons. Okay, so we have done, propped cantilever. Okay, so it is something like propped cantilever. We have done, and then we have found out the bending moments and others. So up to 48, this has reached the plastic moment, but this is still MY. It has not reached the plastic stage. Now from 48 to 54, that is for the remaining 6 kilonewtons. Say. So we have modeled this as a simply supported beam. That means the bending moment at this place is 0. So the 6 kilonewton load set is not carried by MA at all. So only MC will come into picture. So using simply supported beams, we have computed our bending moment diagram and other things. So it is something like your analysis is say. So your beam original it was a propped cantilever, but when it is going to fail, say, so from propped cantilever it has come to simply supported beam, and then hinge formation at the center, and finally it collapses. Okay, so this is how the collapse mechanism say of our propped cantilever. So this is how it happens. So now here one most important thing what you have seen is in the problems here, the first hinge basically. Okay, so this has been formed at A. Okay, now the second hinge say it has formed at the C point. Anyway, there is no third hinge here in this problem. Okay, so automatically you see it has become something like this. So this is our thing. So the most important assumption here is, as already we told you, the stress strain curve, so the moment versus curvature, it is basically curved actually. Okay. So now with our incremental analysis, say, so now it is something like the up to here elastic thing. Once a hinge has formed, say, this is our propped cantilever. Okay, linear analysis only, which we have done linear elastic only. Now once a propped cantilever, say, after propped cantilever, it has become a simply supported beam, and still we have done linear elastic only. Okay, although we are saying it is a plastic analysis, it is something like you are doing it two times. Once hinge has formed another beam, and then you see it has once again we are carrying out the same linear elastic analysis, whatever you have studied in your structure analysis only. Okay, so all that's a plastic analysis, but we have done like incremental linear elastic analysis itself. Can you comment about the stiffness? So in this range, what is the stiffness? In this range, what is the stiffness here? Load versus deflection diagram, when you draw, say, the slope of the curve will give you. So the slope is what you call the slope of this line. So in load versus deflection diagram, so what do you call the slope is indicates what? Slope indicates. Are you there? So what does the slope indicates? Say what does the slope indicates in a load deflection diagram? See, all of you are there. You are able to hear. So what is the slope of that line, in that load versus deflection? See, all of you are there. See, Amruta, Anil, Sohan, Ashwin, Kalyan, Rahul, all of you are there, right? Vani also is there. So what is the slope of the line? Slope indicates, in load versus deflection. So what does slope versus deflection? Slope of that graph tells you. So the slope, what does it indicate in slope deflection diagram? It indicates a stiffness. So P is equal to K times delta V, right? So it is basically the stiffness. So now here, what is your comment on the stiffness? So initially the slope is high, basically. After that, it has become simply supported beam. So what happens is the stiffness reduces, okay, due to this plastic, this one. And finally at collapse, say the stiffness becomes almost zero kind of thing for our these beams. So this is our the load versus deflection diagram, say. So it happens something like this, okay. So this is a very important thing, you should remember, okay. Yeah. So now this is how the graph looks like. So if you draw for this the same problem, say, so 32 kilonewtons, then 40 kilonewtons, then 48, then 54, basically, okay. So now these are the points, say, which this one. So now our first hinge, basically, it has started at which point? See, at 40 kilonewtons, it is still 7.5. At 48, you see the hinge has formed, basically. Okay. So this is where the first hinge has formed, that A, and this is a place where the second hinge has formed. So these are the points, like it has been plotted, the load versus deflection. So these are not the hinges. So at this point, 32 and then 29.17 is the deflection here, and then rotation, say, so like up to 48 kilonewtons, this rotation at A was 0, and suddenly after 48, say, you will see a huge, this one. So if you see this line, it is essentially a straight line, up to the first hinge formation. Okay. So once the first hinge has formed, say, so your beam is changing the mechanism from propped cantilever to simply supported. So the slope of the line, changes essentially. Okay. So this is how the slope load versus deflection diagram, looks like. So if you see the important points here, say, so now the actual load, that is a collapse load for this beam is 54 kilonewtons. Okay, but initially the load, the design load, what was 40 kilonewton. That is elastic limit. So if you try to find out the ratio, say, automatically you can say 35% extra capacity is there for the structure. Okay, and if you try to ignore this extra capacities, you may be inefficient or uneconomical kind of things will happen, basically. And of course, at the end of the analysis, the most important observation was bending moment at A, bending moment at C. Both of them are same and equal to 9 kilonewton meter. That is the plastic moment itself. So this is a very, the important assumption we have seen. So if you try to find out the ratios, MA by MC is 1 itself. Now in an elastic analysis, so MA is 3PL by 16, MC is 5PL by 32. So this is essentially 1.2. So these are elastic analysis. So if you do a plastic analysis, so the bending moment at the hinge points, both of them will be exactly same, and it will be equal to the plastic moment itself. And now the point of collapse is we had 4 reactions, okay, because it's a propped cantilever. Through 3 at the the fixed end and 1 at the that roller support, so 4, and 2 plastic hinges. So finally, you can, if you try to find out how many mechanisms, so R minus C minus 3, so 4 minus 2 minus 3 is minus 1. So which is a mechanism, that is something like one mechanism we have, and of course the collapse happens itself. Okay. And then one more important observation is when the load increases, say, from 48 to 54 kilonewtons. Okay. So now this is a place where at 48, you have the first hinge has been formed at A, the plastic hinge. So now, the main assumption is if the material doesn't have sufficient ductility, that is where the ductility becomes very important. So automatically what happens at A, because it will have, if there is no ductility, say, then, you will have a brittle type of, catastrophic failure, basically. But since the steel has the huge ductility, so it will allow this extra rotation also, and they're allowing the extra load to be taken at sea. So ductility also plays a very large important role here. So if you have like this, because of the huge ductility say, so your A will allow extra rotation, and it will allow the extra load set to be taken care by the that C is itself. Suppose if it is not ductile material say, so something like this, okay, then it just suddenly it breaks. Once A has been plastified, you see, it will just brittle failure will happen, and your whole plastic analysis theory itself will not be applicable for that type of problems itself. So these are some important observations. And we can find out load factor also. So load factor is defined as what is a collapse load, and then what is the working load essentially. Okay, so like for these problems, a collapse load we have obtained as 54, and the working load is 32. Initially the load was a 32 on that one, so it turns out to be 1.6875. So these are collapse load factors, which is widely used in the design itself. And you can also find out the working load and the yield load say, that is at 40 yielding has started, so it is 1.25, whereas the collapse loads it will be 1.6875. So these things are very important for design. Okay, and now now why plastic design is more economical say. Okay, so this graph will illustrate, see why plastic design is economical. Yeah. So this graph tells you. So if you plot the load versus deflection diagram, say, okay. So elastic design is something like this. So the same propped cantilever, and if you do elastic design, say, so in elastic design, the main design load is like this actually. Once the first hinge starts formed, say, that means, the structure has reached a collapse. That is assumption in elastic design. Okay. So you are not allowing, so the first plastic hinge. So the first plastic hinge, when it forms itself, is our design load. So the elastic design goes like this. But if it is a plastic design, say, so we are going until collapse. Okay, so this is a hinge which is formed at A, and this is a hinge formed at C. So we are taking this as our, the design load corresponding to this portion itself. Okay. So that means you are utilizing the reserve strength basically. So whatever reserve strength is there, so from A to C, that is also being utilized in plastic design. But in elastic design, the main problem is you are not utilizing this reserve strength into our calculations. Okay. And now you tell me, suppose if it is a determinate structure, say. So if it is a statically determinate structure, okay. Yeah. Now, what happens? Your elastic design, plastic design, say, both of them, how much difference will be for statically determinate structure, like for a simply supported beam. Okay. So subjected to this load, say. Now, so for simply supported beam to collapse, say, how many hinges are required? See, how many hinges are required for a simply supported beam to reach collapse? Please tell me. See, all of you are there, right? Please tell me. See, how many hinges are required, for a simply supported beam? Just now we solved, right? I think Vani, right? Tell me, how many hinges are required? See, Rohit Singh, can you tell me? See, Manikandan, So how many plastic hinges are required for simply supported beam? So please respond, otherwise, you see, because, we are uploading the videos in YouTube, you understand? So please respond for simply supported beam, how many hinges are required? 2 for a simply supported beam. Subhanshu. So just for a simply supported beam, how many plastic hinges are required? You have mechanical hinges at both the edges. How many hinges are required for collapse?
One.
One. One. Okay, fine. Fantastic. Okay. So now for simply supported beams, okay, so you require only one plastic. These are already hinges. So once hinge forms, automatically, it just collapses. Okay. So now for statically determinate structures, say, what will be this, whether plastic design will have any advantage? See, one hinge has formed for the previous problems. Two hinges have formed. Okay. Now two hinges are there. So in elastic design, the formation of first hinge itself is taken as the design load. Okay. In plastic design, say the formation of the second hinge, say this is taken as your design load. Okay. So that means you are utilizing the reserve strength which is from A to C. Okay. Now if it is a statically determinate structure, say, so now how this graph will look like? So elastic design and plastic design, say, so hinge has formed. Yeah. So now you see it has become like this. Now in plastic design, whether it will have any advantage when you are doing this the determinate structures. So in elastic design, formation of first hinge itself is your design load. In plastic design, the formation of the second hinge, say, that is a collapse thing, is your design load. You followed. So in the previous problem, say the first hinge was formed at I think 40 and the second hinge formed at 54. So now the design load in plastic design is 54. Okay. But whereas the first hinge, say, is a 40 itself. So the reserve strength we are utilizing. If it is a statically determinate structure, say there is only one hinge only is possible here. Now whether plastic design will give any advantages or not. Now any advantage will be there.
Advantage.
So Vani, right? Please once again tell me.
Advantage.
Advantages are there for statically determinate. See, for statically determinate, you have see elastic formation one hinge only. So now where is the reserve strength coming? Where are you utilizing this? That is from A to C. That is for the propped cantilever set. Two hinges are there. So this reserved thing you are taking into consideration. But if it is only one hinge is forming, say, so then you are not taking anything into extra. Of course, you are taking that PL by 4 or whatever here. That is fine, but generally what happens is statically determinate, say you have advantages because your MP by that L that comes into picture, but generally it will not be that much advantages for statically determinate. But if it's indeterminate structure, so you will get maximum advantage if you do this plastic design. Okay, that's just here also you have advantages, but here advantages are more because this extra strength also is being taken into consideration. Okay, that is the main advantage. And now let us, whatever we have done, so the same problem, let us do it very systematically. So the same propped cantilever, say. So it is subjected to an increasing load. Okay, generally to find out the collapse load, so 10 is a working load, say. Okay, so we want to find out the collapse load. That is, we write in terms of alpha times P. So this is what we call as the load factor. So this has to be calculated for this. What is the collapse load and what is the load factor? Okay. So the length is 12 meter has been given. P is 10 kilonewton. So the load is all 10 alpha. So this is the load which is acting on the beam. And the plastic movements is 27 kilonewton per kilonewton meter. From the experiments, they have got this one for the beam. Now we have to find out what is the alpha value at collapse, or we want to find out what is the maximum collapse load for this beam itself. Okay. So now how do we do this type of a problem? Whatever method we did previously for the same propped cantilever. So here also we do like incremental method we say. Okay, so what we try to do is like this. So now initially, you assume alpha to be 1. So, we don't know any this one. So alpha is 1 means 10 kilonewton itself is my collapse load. Okay, so now let us calculate the bending moments. So we already know for this problem. So the first iteration, say MA1. So this is 3PL by 60, the same expression, say, which we used. So this becomes, so 3 into 10 into, 12 by 16. So this turns out to be 22.5 kilonewton meter. So this is a bending moment at A. Now in the first stage, okay. Now bending moment at B, say. So these are the two critical portions where bending moment will be all high. we already seen previously. So this is a 5 PL by 32. Okay. So substitute everything. Say. So this turns out to be 18.75. Yeah. So 18.75 kilonewton meter actually. And you can calculate even the vertical deflection also at B, that is a delta. So this expression also okay. Yeah, so this delta B is 7 PL cube, which you have already studied in your structure analysis course 768 EI. Okay, so this turns out to be 157.5 by EI. So this is a deflection actually. So this is our stage 1 analysis. So just for ordinary load, assuming alpha is 1, we have calculated all these numbers itself. Okay. Now the load factor. So now for the section A is place here to become plastic, say. So to become this plastic, okay, how much alpha is required? Say alpha A, I am writing this as alpha A1. So this is MP by MA1. Okay, so this turns out to be 27 by, you say, 22.5, say 1.2. Okay, so for alpha A to become plastic is 1.2. Now for B to become plastic, so that is alpha, B1. So this is, MP by MB1. Okay, so this also, if you try to calculate, this turns out to be, you see, 1.44. Okay, so this is the load factors actually for B to become plastic and for A to become plastic, say. So this becomes 1.2. So now which one will become quick plastic as you keep increasing the load? So obviously it is A itself. So what you have to do is, so the lowest of these two is, 1.2. So lowest of alpha A1 and alpha B1 basically. So it is 1.2. So this is my load factor, which comes from the stage 1 analysis. So this we call as stage 1. Because it's indeterminate structure, say we have to do it in stages. Okay, so all of factor is 1.2. Okay, so now we calculate the remaining the things itself. Okay, so with 1.2, say, so the bending moment at A becomes so the load becomes so the load becomes alpha 1.2 into 10. Okay, so that is a 12 kilonewton basically. Okay, and your MA, the bending moment at A becomes 1.2 into 22.5. So this is a 27, and bending moment at B, say. So this will be 1.2 into 18.75. This is a 22.5, and then the deflection at B. Okay, now previously the load was 10, now it is a 12 kilonewtons. Okay, so this becomes is a 1.2 times into 157.5 by EI. Okay, so this is 189 by EI. So these are the analysis. Okay, after using this load factor. So now what has happened is, so our A has become plastic, but B is still in the 22.51. It has not still this plastic itself. Okay, so now we have to do stage 2 analysis. Now, since our A has a plastified cell, so our assumption is once a point has plastified, it will not carry any more extra load actual. Okay, so this becomes like a hinge. So this is our hinge. So it is something like our simply supported beam itself. Okay, now here at this stage of calculation, say, so A becomes a hinge. Okay, and the beam becomes like a simply supported beam. Same thing, whatever we did previously. Okay, and now so for this problem, say, so you take P is equal to 10 kilonewton, whatever is the load, assuming alpha as 1. So for P is equal to 10, so you find out the bending moment diagram. So the bending moment diagram at A anyway it is 0, at PL by 4. So 2 stands for stage 2 analysis. Okay, so this turns out to be 30 kilonewton meter. Okay, and then the deflection, say, at B. So this also comes from PL cube by 48 EI. So this turns out to be 360 by EI. Okay, so this is one. Now for the section to become plastic, say, so now we want B also to become plastic. Okay, so this has to become plastic. So for B to be plastic, how much will be the load factor? Okay, so this alpha B2 has to be found out. Okay, so this we have calculated for 10. Now we have to normalize actual. So we write this as all MP alpha 1 into MB1. Okay, my divided by M0. This is required because we have taken the load as 10. You can take load as unity and also you can find out. So this turns out to be MP is 27. Alpha 1 is 1.2 into 18.75. Divided by M0 is 30. So this turns out to be 4.5 by 30, say. So this turns out to be 0.15 actual. So this is the multiplying factor or the reducing load factor, for the second stages. So if you take 0.15, so now the total movement at B. Okay, so this becomes, initially it was 22.5 plus 0.15 say into, this is 30. So this turns out to be 27 kilonewton meter. Okay, and the total deflection say delta B. So this comprises of the previous one, that is 189 by I, okay, plus 0.15 is my multiplying factor, into is 360 by EI, which comes from the simply supported case. So this you can write this as 243 by EI. Okay, so these are the final numbers itself. So now MB is also 27, MA is also 27, and if you plot the deflection load versus deflection, say, so this is a point basically. Okay, so where the first hinge has formed at A, and then the second hinge has formed at E. So now the total load factor, say that alpha is alpha 1 plus alpha 2, both the things have to be taken. So this becomes 1.2 was initially plus 0.15. So the load factor is 1.25. So this is how we can calculate systematically. Sorry, 1.35 is the load factor. Okay. So this is how we can systematically calculate the step-by-step analysis itself. Now this you can easily do it on a computer, or you can make a spreadsheet, and you can do we can make it right in terms of the nice tables kind of thing itself. Okay, the Excel sheet itself. Yeah. So you can see, so this we will write it. So there are several steps are there. So we can see, like, we have this, you can write it in a table, column 1, column 2 kind of thing. You can write this one. So like just the stage 1. So 2 stages are there for this analysis. Okay. Stage 1. You can tabulate nicely. Okay. So now you are having two. So this is my beam, say, fixed one, and the load is here. So this is A, B, C. Now we divide this into two pieces. That is 1 and then 2. So we have A and B. So one portion of the beam is this portion. Okay. And this is the second portion. So we can nicely tabulate also. BC. Okay. So these are this one, and these are the joints. Okay. So you can put it in a nice, the table kind of format actually. Okay. And now the bending moments say. So initially, due to the 10 kilo, assuming alpha as 1. Okay. So we got, so this was, I think the movement was 22.5. At B, it was 18.75. And same thing only. To be in equilibrium, we write negative. But anyway, at C, it is simply supported. So it is 0. So this is the original bending moments. Now the residual plastic moments, so when I is equal to 1, so these mi's can be taken as 0, that is m1s. Okay, so these are iterative, m1 is taken as 0. So the residual plastic moments say, so mp is 27 minus 0, 27 minus 0, 27 minus 0, so 27 minus 0. So this is a residual, this one. Now we have to find out the load factors, that is this divided by m0. So that is a 27 by 22.5. Okay, so this turns out to be 1.2. Okay, and this one turns out to be 27. Yeah, 27 divided by 18.75. This turns out to be 1.44. Now same thing only, 1.44, and of course this becomes there is nothing actually, because it is already a hinge actual. And now the cumulative moment distribution has to be taken. So that is m2. Okay. So m1 is 0. Then the starting stages, m1s are all taken as zeros itself. So this becomes 0 plus alpha, the lowest factor you have to take. So the lowest among 1.2, 1.44 is, the lowest is 1.2. So 1.2 times 22.5. So this turns out to be 27 kilonewtons, and this one say, so this will be 0 plus 1.2 into 18.75. So this turns out to be 22.5. Okay, so this is also 22.5. Of course, minus sign is there, and this is 0 actual. And you can, if you want, you can compute the deflection also. You can easily calculate, the deflection also. Okay, so this is our stage 1 of the analysis. Okay, now the next stage, the second stage also, you can easily write this one. So same thing, 1, 2. So you have A, and then B, and then C actual. Okay, so you can write it in a nice table kind of format, incremental. And now the analysis say, so now this beam has become a simply supported beam. Okay, so because already hinge has formed at this place, so now this is a simply supported beam, and load is a 10 kilonewtons only. So now what is the bending moment at A, because already it has plastified. What's the moment at A? Because it has already been plastified. So what will be the bending moment at A now? So what's the bending moment? So this is 1 and this is 2. Okay, so A, B, C. Now in the first stage of analysis, so now A has been plastified. Okay, so now yeah, bending moment at A is 0. Now that is M naught basically. Okay, so now this that the B is a 30, of course minus 30 and then 0. Okay, so these are this one. Now the residual plastic moment say. So this is MP minus MI. Okay, so that is your 27 say minus mi. Mi is in the previous graph. So this is a stage 2. So this becomes m1 or m2 kind of thing you have. So this is a 27 kilonewtons you have. Okay. So this 27 minus 27, it happens here. Now for this B say, so now this also becomes a 27 minus the residual moment which comes from the previous curve. So that is a 22.5 itself. Okay. So 22.5. So this turns out to be 4.5. Similarly, here also 4.5 here, of course, negative sign we just put. And anyway, this is 0 actual. Now, once again, you compute the load factors. Anyway, the first one, there is nothing here, the load factor or whatever here, because everything is 0 itself. Now, for the second one, say, so the load factor is 4.5 by 30. So this turns out to be 0.15 actually. So same thing here also 0.15, and of course these are all there is nothing for this this place because already it is a hinge itself. Now the cumulative movements is anyway this will be simply 27 itself, and now this becomes m. So that is a 22.5 plus 0.15 into 30. So this turns out to be 27. So same thing here also 27 0 0 you have actually. Okay. So, and of course, if you want, you can find out the deflections and other things also. So now here you can see. So now B also has plastified actually. Okay. So here the load factor, the critical load factor is 0.15. So now in the previous stage 1 of analysis, the critical load factor was 1.2. So you add these two. So 1.2 plus 0.15. So this turns out to be 1.35. So if you want, say, this whole analysis, you can write it in nice tables itself, and the summation of this, the first stage what load factor you have got, the second stage what load factor you have got. So if you add up, you will get the total the factor itself. So 1.35 is our load factor. So the collapse load say for this problem is alpha times P. So P is 10, so this becomes is 13.5 kilonewtons is our the collapse load actually. Okay, so this is how we can find out in terms of simple this incremental method in a step by step the method itself. Okay, so this helps you. Okay, the same Excel sheet I'm showing, and now we have to find out collapse load factors for this portal frame actually. Okay, so this is the load initially. The working load is a 40, and alpha is your collapse factor, and these are the details has been provided. So length of this beam is 6 meters, and then you have 3 meter here and 2 meter here. So this total column says a 5 meter length here, and here it is a 3 meter length here. And now you tell me what is the indeterminacy for this portal frame? What is the indeterminacy? You have studied in structure analysis, right? What is the statical indeterminacy here? So it is indeterminate. What is the statical indeterminacy of this portal frame? It is fixed at the bottom. Tell me what is its indeterminacy? You have studied in your analysis course, right? Tell me how many unknowns are there, how many equations you have. So at fixed and say how many unknowns will be there?
3 unknowns.
3. So 3. Now tell me what's indeterminacy. So 3 plus 3 6. Total reactions are 6. Now how many equations are there?
3 equations.
So indeterminacy is
3.
3. So now how many hinges are required here? See, the propped cantilever indeterminacy was 1 basically. But after during collapse, how it collapsed? How many hinges formed for a propped cantilever? This problem. Yeah. So this problem, it is also indeterminacy is 1. Okay. And now how many plastic hinges formed for this? at collapse state, say. No. So this problem, how many plastic hinges formed? You know how it collapsed. How where what points plastic hinges formed? See, one plastic hinge is sufficient. See, for complete collapse of this propped cantilever, say how many? Just now we solved, right? How many plastic hinges?
1.
One. How many plastic hinges? This problem, whatever we said, how many plastic hinges was formed to complete collapse of this beam? Simply supported beam, it was one. But for propped cantilever,
It's 2.
two, because at A, as at the fixed end also you should have, at B also you should have. You followed. So two are there. So that means if redundancy is one, say, okay, so the number of plastic hinges required for complete collapse of the beam is you have to add one more actual. So 1 plus 1 becomes two. Okay. Now if it is simply supported beam, say, there is no indeterminacy. So how many plastic hinges are required? Only one. But for propped cantilever, redundancy is one, say, two are required. Now for if the redundancy is for these problems, three is a redundancy, say, okay. Now how many plastic hinges are required? By using the same logic, how many are required?
4.
Four hinges are required actually. Okay. And what are the points where hinges will form in this portal frame? Can you guess, like where hinges, where the bending moments will be high, where the hinges we are going to form in this propped cantilever? Without doing just can you your analysis thing, if you utilize, say, where what is the possible locations of this four plastic hinges, possible locations. Suppose if I write this as A, B, C, D, or 1, 2, 3, or whatever, say. So where plastic hinges will form generally for portal frames. So where bending moments will be high in a portal frame, and of course here the load is also acting at the the joint itself. It is not acting at the middle or something. Suppose if it was acting, the load was acting like this, say, you can say that hinge will form here. But now this problem, load is not acting at only at the junction. Now tell me where hinges are going to get formed without doing the analysis. Can you guess?
B.
B, that is here. Okay, very good. But how many? But this is not sufficient, no, for collapse. So one hinge forms also because it's fixed, right? Everything. So it is still, the portal frame is stable only. Now, so one hinge is at B. Now for complete collapse, you require four plastic hinges. Now where are the remaining three?
C.
C, excellent. Okay, then two more are required. No, one is at B, one is at C. Then. So if it is at B and C also, there is nothing, no collapse. You followed it as like a simply supported beam only. Okay. But still it will be stable. Two more hinges are required to make it unstable. Where are those remaining two?
In between AB.
In between the
AB.
AB. In between AB, you will have, see, this AB is like a cantilever. So this is your load cell. Now where hinge will get formed in a cantilever? Or where the bending moment is high in this portion? In between A and B, or where it is? So in between A and B, where bending moment will be maximum? You just imagine like a cantilever, where bending moment will be maximum. Where, not between A and B, where bending moment will be maximum. Just guess, correct. You.
Yes.
Excellent. Okay, at the support itself. So three hinges, one C, then B, then A, but still the things are stable only. You followed. So one more hinge is required because you require total four hinges for complete collapse of this portal frame. What is the next place?
D.
D, excellent. Okay, so four hinges are required. So now we already know before even doing the problem itself that four hinges are required for complete collapse. Okay, of this portal frame, and these four hinge locations also approximately we have located. Okay. So anyway, so I will stop here. We will continue in our tomorrow's class actually, and we will see step by step incremental thing. So how this portal frame is going to collapse. Okay, so fine. So I will stop here. So if there are any questions, you can ask me. Yeah, stop recording.